Hey there YouTube, I got a video here about a project I'm doing to repair what amounts to a brand new MASTERCOOL Model 967 vacuum pump. Now the vacuum pump is very well built. It's when I first got it, I tested it with a vacuum gauge, a MASTERCOOL brand vacuum gauge. It was 6 microns absolute, 6 microns of mercury absolute, which is, in plain language, that's very, very, very low absolute pressure, or high vacuum. These words get tricky because high vacuum means one thing one time and another thing opposite another time, depending on who's using it. So the convention is the values are given in absolute terms for vacuum, that for laboratory work or high vacuum, or when you want to almost take out basically as much gas as you can out of a system. So 6 micron, lower the number the better. Now this pump ran about 3 hours, and then this happened. It's a motor. This is part of a motor coupling which has two 8-splined pieces. They're identical, and they are connected with this plastic piece. And evidently the plastic piece got hot and melted and just sheared away. One set of splines just reamed that out, so no longer could the motor drive the pump. One of these aluminum die-cat, whatever they're, not even aluminum, pot metal pieces went on that stub shaft. Another one went on the motor shaft, and that plastic piece was assembled so this connected the two, and no good. So solution is get something that's really beefy. This is a little bit bigger as far as length. Instead of 1 5/16, it's like 1 3/4, so it's just about the right length. It has 4 set screws total, so it can, in this case, it can bear down on the flats of the motor the flat of the motor shaft, and the flat that's on the stub shaft coming out of the actual vacuum pump itself. That'd be a load side. And 2 more screws, so it can even be tightened down further. The tightening torque on these 1/4 inch 20 set screws is 87 inch-pounds force, and I do have a torque wrench to do that. So I get all 4 of those real tight. And that should effectively eliminate this completely. It was like trying to find that part. Nowhere in the United States, nowhere in Southern California did this part exist. It had to come from back east. That's beyond ridiculous. If you had an air conditioning service center or whatever, and you had this thing, yeah, right, I'm going to pay overnight delivery of $30 to get a $20 part, just because they can't keep something like that in stock, and it's a piece of junk anyway. So it just doesn't go with the rest of the motor. Now to figure out which one of these I needed, it was pretty easy. Shaft diameter, length, of course there's only a certain length, was the main components, and to make sure that it could take the torque because these do have nicely, the one thing they do nicely have is a D-shaped hole to match up with the flats on the motor shaft and the flat on the pump shaft. You just can't find those. They must be custom built or something, because D-shapes don't exist. So what the people use is a round, they call it round shaft, even though the shaft's not really round. They consider it that. The problem with this is, though, sometimes they get loose and they strip out the the flat, and we've all seen that, right? If we work around this kind of stuff at all, kind of fan motors or something. So the torque capacity of this, we had to figure out, okay, what is the torque rating, because they specify these in terms of torque, and this one's about as good as it gets because it's solid steel. It has a torque capacity of about basically 20 foot-pounds. At 235 inch-pounds, it was about 20 foot-pounds. Now, is that enough? Well, if you're in doubt about your motor, the torque that's going to be imposed on the shaft, on the coupling, by the motor, if you know the horsepower, you probably don't know the torque offhand. Here's something to help, and this is for English, and so that first top there is a truism for both, whether it's the imperial English system of measurement, or if it's the standard units of international system of units, SI, or commonly called the metric. The statement is power of a rotating shaft of any kind, a rotating member, is proportional. That's that trying to be a lowercase Greek letter alpha there. It's pretty messed up. Is proportional to the product of the torque and the frequency of the motor. Well, frequency is another way of saying revolutions per minute, or revolutions per second, or revolutions per day. you could use different, and that's where it comes down. That's why it's a general proportionality statement. No matter what the units of measurement are for any or all three of those things, if power will be in a power unit, torque will use some unit of torque times some unit of frequency will equal some unit of power. Well, we don't want to just deal with Joe. Yeah, I'm going to use Joe Simpson's the torque he applied during a famous arm wrestling match, measured by a special meter, and call that from his elbow to his hand, that convert that to a torque value, and then use that for torque. And for frequency, I don't know, maybe these standardized drip of water I had in the backyard, or whatever. You can make up whatever you want. So civilization has come up with, there's basically two competing units. The imperial is power in horsepower equals torque in pound-force feet, foot-pounds to many people, but it's really pound-force feet, divided by 5252, and that 5252 comes from 33,000 being divided by twice pi. So that's where that constant comes from if you're interested. But that is the formula to get a quality of horsepower equals torque times RPM. And RPM's the frequency chosen in this case by almost everybody, revolutions per minute's a pretty standardized unit. It actually crosses over to the SI system, or the metric system, as this. Same proportionality, nothing changes there, but instead we choose power equals torque times RPM divided by 10. I didn't write down the units there, but power in this case is in watts. P is in watts, and then T is in Newton meters. RPM is the same as RPM in English, and the constant divided by is 10, which is, the exact figure is 60 over 2 pi, but it's pretty close to 10. So either one of those ways you could compute the other. We know two of the factors, RPM, torque, power, any two, you could figure out the other one. Just simple algebra. So in this case, you run that through the English formula. You got a half a horsepower times 5252, boils down to 2626. 2626 is equal to the product of torque and RPM. Well, I also know the motor's RPM, its rated power, occurs at 1725 RPM. So I end up with about 1.5 pound-force feet if I solve the algebra, which translates into, in terms of inch-pounds, 18. Now that's at full load, okay, the motor operating at 100% load. Now this is a capacitor start motor, not capacitor run, not permanent split capacitor, not shaded pole. It is a capacitor start motor, and according to the internet search I did, it can have, we'll just call it 400% of its rated torque. Can be, if you try to slow it down under load, it'll peak at about 4 times that rated torque before it starts to stall out. So I just said 18 inch-pounds times 4. That would be, it'll end up being 72 inch-pounds. Okay, this is rated for 240, so it has a more than enough safety margin for this application. As far as it should hold up, no problem. So what I'm going to do is, I'm not going to show the video of installing this thing. It's pretty easy. I'm going to just have to clamp this onto the shaft, sort of center this with the two halves reconnected, put it in there, put the motor and the housing back together, get it centered, make sure I got that one of these two sets of screws squared up on the motor's flat of the shaft, and the other squared up on the flat of the shaft, so it's a nice straight dig in. Torque it at 87 inch-pounds, and then wherever these land, torque them to 87 inch-pounds, and should be good to go. And then the next thing will be a showing the view of it assembled. I'll probably show an intermediate view with where it's ready to be tightened down, showing this thing in place. Intermediate video here. I used this with this nice D shape to grab onto the shaft of the pump, the stub shaft, and then rotate the flat so it's facing directly where I can access, or I can get the socket Allen key in there and tighten it down. So that is the location, and the other set of screws that will be bearing down on the shaft, the round part of the shaft, are here. So I just wanted to show that. That's the first step, is to get that aligned. The motor will be done the same way, but the motor shaft I can spin by hand, right, because it's just a motor. This thing's a little more difficult. It's easily spun with this. as a grab on, but it would I could even spin it with my hand if I sit there and try to be strong and strain my hand. But anyway, that's that part. Okay, so far so good. The coupling is in there. It's well engaged onto along the length of the motor shaft. It's also well engaged along the length of here. So it's just about perfect. I'll get the Rutland part number of this. It's Rutland brand. You can get it from Granger. I got it from Amazon. I think Amazon sold it through Granger, or Granger sold it through Amazon. Anyway, it's pretty easy to come by. It just took a little bit of research to find the right size. So I'm going to finish torquing everything up, and then it'll just be a matter of plugging it in and seeing what happens. Another intermediate step to ensure that the motor, this is a well-machined system, right? You can buy motor couplings that have flexible components to them to allow for some shaft misalignment. This doesn't need that. It's machined. It's a housing. The motor does have a bit of play associated with the fact that these 4 long bolts that go through the motor and into the housing here, here, and the other 2 around the other side. There's some room for moving it around. So what I'm going to do is torque all 4 set screws there, and then tighten these where the motor wants to finally be exactly centered. That's where it'll be tightened. So that way it'll be a good alignment, no need for flexible coupling, and it'll just be ready to go. It's that's torqued to, the coupling, all 4 set screws are torqued to 87 inch, well, 90. I got a wrench here that reads down to the 5 inch-pound division, so I just observed 90 and that was it. And that is, I'll tell you, that is about the maximum they're going to take, because the Allen key socket thing, you know what, I don't know if he's American made. It's Chinese made it, maybe an American one with harder steel, but it was getting close to being the limit of the torque what it could take. Now I left these 4 loose. You can see the motor is still, it can rotate circumferentially, rotating around the axis, but it won't move. I can't move it like, XY axis. So what I'm going to do is just nicely, I'm going to position it on the table so that it's resting. I don't think I'll do that actually, because that's going to just impose load that would tend to off center this. So I'm just going to, about halfway between the two tinks, or it makes a noise either way you turn it as it comes against its limit. Center it about in the middle there. Get a socket, and I'm going to torque these. I don't have a torque spec on these. Are tiny bolts. I'm just going to snug, and that's what I'll do, and then it'll be vacuum test next. Okay, fully assembled, couplings installed, like probably 1032 screws along, 6 inches long or so. They're installed. Units ready for testing. So we're going to get the vacuum gauge and also the extension cord to power this thing, and we'll just see. I'll let it run for a while, and it's got fresh vacuum pump oil in it, plenty full. It's ready to go. And what my vacuum gauge will be is on the there's 3 size connections here. There's the ones you see in refrigeration are the old R12 systems, and the gauge sets fundamentally have this 1/4 inch flare. And then you also have the 1/2 inch Acme, which is the ones from 1/4 inch flare, 1/2 inch Acme, I think that's 3/8 flare. And this is what HC 134A, ever since 1990, I think January of 93 or 94, is when the automakers in America had to have that HC 134A. I'm sorry, R134A, not HC, R134A. And so you find gauge sets that fundamentally still have this connection, but they they adapt to the R134A system with quick disconnects that use a special connection that isn't. They don't even use it on cars. They don't use the direct screw on cars anymore. They use a snap connector, a quick disconnect, and that's adapted to our 12 gauge set. So the connections that an R12 gauge set would have. And then this is used on the manifold gauge set for the center tube that's for the evacuation, or for providing the refrigerant to recharge. So you do have to have that fitting if you don't want to to with a gauge set that I have at least, to furnish the a direct connection to the vacuum pump without an adapter. That's good. And then when you go to charge, there is a similar connector on the gauge. You use that same hose that connects to the vacuum pump. You take it off the hose, put it on the refrigerant can, bleed it, make sure you just got all the air out of it. And then there's a whole procedure to that, but you basically introduce the refrigerant. I happen to have a refrigerant weight scale, mass scale, to charge by weight, so it's no guessing about gauge pressures or atmospheric temperature or any of that stuff. It's just hard vacuum, good vacuum, then introduce the mass of refrigerant, and according to the factory manual, and you are done. So it makes this kind of it's like everything else in life, the right tool makes the job, given job, a lot easier. So anyway, vacuum performance, going to test it with the vacuum gauge. I would expect something 30 microns or better based on this repair. Okay, here's the test. It's ready to test. I've got AC power over here, and I'm putting an AC adapter to the vacuum gauge. Doesn't need that. It's battery powered fundamentally, but keeps the battery from being used. It is a same company that made the pump, MASTERCOOL. It goes from atmospheric. If anything above, I think it's 20 millimeters of mercury, 20,000 microns. Anything above that level of absolute pressure, it just gives the dashes with ATM. So this is a low, very low pressure gauge. It doesn't even start taking readings until 20 millimeters of mercury. 1 atmosphere is 760 standard. And so you're looking at 140, 130, 138 of an atmosphere before it even begins to record display values. So it is a low pressure gauge. Okay, so here it goes. Gas ballast is open because they say to do that to keep the cartridge in there from breaking. But I think it's a piece of metal. It's heavier than, I think it seems to be heavier than the motor. It's just it furnishes most of the weight of this unit. It is a solid cube of metal, so, but it could have veins in there and so delicacies that cause it to have problems if you don't open the ballast and gradually let the vacuum build instead of a sudden vacuum building, or too much. Maybe it's for too much gas flowing through. Make sure I got my exhaust cap off. While it's running, I may go get some pliers. And this is hand tight. It's pretty well knurled, and for what I'm doing, it should furnish this is the only thing that's the leak could be is here. Otherwise, this thing's well sealed up. I'm going to open the valve that exposes the vacuum pump mechanism to these ports and make sure it's all the way open. Just lightly, fully open. Oil. That's where you add oil. Okay, here we go. Power on. Oh wow. That took the ballast all the way up. That didn't happen before. So that coupler, that piece of junk, was a problem from day one. Really, they need to do something like this. Here's the Rutland part number. SCX. SCX means it has no keyway in the coupler. Although the ones with the keyway still have the set screws. So you can get away with this thing with either one. And it's -8-8-F. That's the exact part number I'm using from Rutland. So make this $26. It was $26, including the free shipping, and it was Amazon Prime 2 days, instead of $20 at least for this factory junk to just do the same thing again. So no problem there. All right, so I'm going to start closing the gas ballast slowly. I think I saw 30 millimeters of mercury there. Let me open this all the way up again. 20. So I said 20. It starts taking readings. It may go up to 30, 40. I think I was wrong. It's going to be 40 millimeters of mercury. So 1/20th of an atmosphere. 1/15. So I'm closing it all the way down. So for air conditioner work, for example, on my Jeep, the specification is, and it's where you got to be careful with vacuum, they specify 25 inches of mercury. That is not absolute pressure. That is gauge pressure. So what they're saying is they want to see 20, even regardless of the altitude, I would imagine, or maybe there's some, they would probably say there's a correction even for that. Let's say it's sea level, and here in California we're pretty close to sea level. They would show that the gauge reading, in other words, the difference between the atmosphere and the system, the refrigerant air conditioning system, is 25 inches difference in pressure. Well, if you're at sea level, that's going to amount to an absolute of roughly 5 inches, which is actually quite a bit of, in this case, it's 125 millimeters. So this thing would be way off scale. It would be 125,000 microns. That's what Jeep allows for the 2004 Grand Cherokee to have that's the level of vacuum. So they allow a lot of air to be left over, a lot of old refrigerant, a lot of air. Not a very rigorous spec. This thing, as you can see, is below 500. That's half a millimeter, or rough figures, 1/50th of an inch. 1/50th of an inch. So instead of 4 inches, 1/50th of an inch right now. Capability of this pump. And typical vacuum level I found on this is when I was even working with this crummy thing, was 16 millimeters of mercury, which again, a lot lower than the 125 millimeters or 5 inches of mercury. 125 millimeters or 5 inches, the same basic thing. So yeah, this thing's very capable, way more than you need for automotive refrigeration, really. With tightening all these little connections up, it should allow for an ultimate pressure of vacuum pressure, because we're talking in terms of its absolute pressure. 30 microns is what I had before. So, it looks like I would have no problem getting that. Okay, like I was telling you, my battery's going to die, so I'll sign off here with this. This is basically a modification of a pretty good vacuum pump, aluminum construction, model 967, but it's sad that I think I paid a little over $300 for it, and that was the best deal I could find. A lot of people are asking $500-600 for these things. I don't know how to do that, because people have got to know that. Don't they know that they're going to just punch in an internet search and find it for like nearly half that price? So, but anyway, they do. And for that good of a pump, you got to be kidding me, right? I mean, if they're worried about, say this thing jams up, well, whatever. If it jams up, yeah, they might say, oh, it's a mechanical fuse. It's really not, but say it jams up, oh well, so what? Things jam up all the time, and they don't have this kind of crummy part associated with them. So half a horsepower on that pump isn't going to hurt anything. Like I said, lock rotor peak torque of this motor being brought from operating speed to standstill would only be 72-inch pound force. 72-inch pound force. And this steel coupling is good for 4 times that, and nearly 4 times, and it's impervious to heat. As we all know, plastic is not. Hope this helps anybody out there with a MASTERCOOL pump that has a coupler between the motor and the pump. Again, a lot of vacuum pumps, maybe they don't even have this issue. They just one casing with the directly connected internally, and you never run across this. But these more professional heavy-duty systems have motor couplings. Okay, so great. That's great. But just using motor coupling that makes sense and isn't a piece of junk. Bye for now.